In my previous video, I assembled a circuit that produced super high voltages using a flyback transformer. While it was a simple design, you may be quick to realize that the method falls short when it comes to efficiency, mainly due to the switching losses. So today, I am going to build a circuit that overcomes that, and as a bonus, it can be used for multiple applications like induction heating, which is a non-contact method of heating metals, as a flyback driver, which can produce very high current and high frequency electric arcs, and finally, as a means of wireless energy transfer. So, without further ado, let's get started. This circuit is based on the infamous astable multivibrator, which employs two similar bipolar junction transistors to produce free running square pulses at a particular frequency and duty cycle. The only difference here being the use of MOSFETs instead of the BJTs, and the output is sinusoidal instead of the square pulses. This is achieved by utilizing the power of electrical resonance. To appreciate the role resonance plays in this circuit, we must first have at least a broad understanding of the phenomenon. As we all know, everything that is physical around us has a natural frequency of oscillation. When you excite them at the exact same frequency as that of their natural frequency, the object responds by oscillating at higher amplitudes, much higher than they would normally. If you think of it, you'll realize that it is true with people as well, or with any living thing for that matter. Anyways, when resonance occurs, the system is able to store and release huge amounts of energy, going through a cycle of give and take that sustains this energy transfer back and forth between the two storage modes until it dies out eventually owing to the losses in the system. A familiar example would be a simple swing that we all like to play at parks and playgrounds. Likewise, in electric circuits, the basic elements, namely inductor and capacitor, are able to store and release energy between them. The inductor does it in the magnetic field, whereas the capacitor does it in the form of electric field. When you connect them in parallel and excite them with a signal that matches their resonant frequency, the resulting energy transfer between the L and C components of the tank circuit creates oscillations that are able to reach amplitudes much higher than they would at other frequencies. In short, during resonance, the impedance of the circuit disappears, making the transfer of energy much greater. So much so that you have insanely high voltages and currents in the circuit. Of course, this is just the reactive power, mostly used to create the electric and magnetic fields. Nevertheless, they can be pretty high. This is the power of resonance. With that understanding, let's see the components needed for the build. Now that we know what resonance is, let's briefly understand how a circuit works. This is a schematic around which I built this circuit. A link to the PDF version is available in the description if you want to download it. Other important points are given in the attached schematic, so I'm not going to talk about them here. It's pretty self-explanatory. People say no two individuals are alike. The same is true here. The initial kick to the oscillations is provided by the fact that one MOSFET is more likely to turn on first than the other due to its inherent property. It is very difficult to predict which one, but one of them usually gets the ball rolling. The two LEDs between the drain and source indicate exactly this, and if any one is glowing but not both, then you know the circuit is having a starting trouble, so you can quickly turn it off before frying the MOSFETs. If you ask me what happens in the circuit that leads to resonance, well, I have two choices. Option 1, contain everything in one word, quote unquote, resonance action, and skip the boring part to increase the watch time of my video. Or option 2, deliberately make this explanation a bit detailed so that you can take away something from this video. So, the red pill or the blue pill scenario, isn't it? Well, this is in the Matrix, and certainly I didn't enjoy the latest edition of it. So, as usual, welcome to the nerd way of learning things. When you switch on power to the circuit, let's say Q1 is the first to turn on. Current flows from the battery through the filter L3 into the winding L1 and through the drain of Q1 into the source, thereby pulling down the drain potential to 0 volts. Due to this, the gate of Q2 discharges via diode D4 to ground, ensuring that Q2 remains off while Q1 is on. Let's say that the current through L1 creates a voltage V across it, like so. Now that it's a center type winding, and because the sense of the winding are the same, a voltage V is induced across L2 as well due to transformer action, effectively making the voltage across capacitor C1 2 times that of V. The current has nowhere to go now except charge the capacitor C1, which gradually charges up to its peak value of 2 times V. Once the capacitor is fully charged, it tries to discharge into the inductor formed by L2 and L1. If you recall the resonance animation you saw earlier, you might be able to visualize this much better. Now the capacitor discharges into L2 through L1 until the voltage at the drain of Q2 reaches 0. When this happens, the gate of Q1 discharges via diode D3, turning Q1 off, ensuring only one MOSFET among the pair is on at a time. Now the same cycle repeats itself but in opposite direction via Q2 and so on and so forth. This is how you get a sine wave across the capacitor C1. If you look carefully, the inherent nature of the resonance circuit is used here to turn on and turn off the MOSFETs only when the voltage at the drain is 0 volts. This is called zero voltage switching. Let me try to explain that with an example. Have you ever tried to jump out of a moving vehicle? Well, you definitely shouldn't, but for the sake of understanding, you could do it much efficiently if you had the patience for the vehicle's speed to reach 0 and then jump. Otherwise, you would end up breaking bones and losing a tooth or two. The same is true here. The switching transistors only turn on or off during the zero crossing of the sine wave, and hence there is ideally zero switching losses. Because even though the current is not zero during the switching, the power that is the product of V and I is always zero, reducing the switching losses and improving the efficiency greatly. Not to mention the gratitude the MOSFETs owe you in return for putting them off their misery. Now let's get on with building the circuit. Now that we have built the circuit, first let's test it as an induction heater. I have experimented with different sizes and types of coils, also with different metals for heating. Each gave different results. Basically, the heating depends on the type of metal used and the resonant frequency. The higher the frequency, the higher the eddy current losses in the metal in the form of heat. Also, the quicker the heating process. One thing to note is the insane amounts of resonant currents in the LC tank circuit, mostly in the order of tens of amperes. Basically, the coil functions as the primary of a transformer. The inserted metal acts as a short-circuited secondary, which produces eddy currents in it. These currents cause immense heat in the metal due to the eddy current losses, thereby heating the metal in an incredible display of fire and fury, which for some reason I don't seem to get enough of playing with it. Next, the same circuit can be used to produce super high voltages using a flyback transformer. I used 6+6 turns of 1 mm square area of cross section electrical wire wound on the exposed ferrite core of a flyback transformer. In both cases, the winding must be in the same direction, or else the MOSFET will give you the magic smoke. Unlike my previous video, this one is pure sine wave and hence the arcs are incredible on the secondary side. These flybacks that I use have a series diode on the secondary, so the arcs are halfway rectified. Nevertheless, they are quite powerful and much hotter and dangerous. So don't play with high voltage if you don't know what you are doing. I could probably use this circuit to make a Tesla coil as well. The applications are vast and your creativity is the only limit. Give me a second here. This is so cool and I just can't stop doing it. Look at these arcs. Incredible. Scary but incredible. Next, let's test it as a wireless power transfer device. I had these through-hole inductors and some LEDs lying around, so I connected them in parallel and now we have a passive power source. When I bring the circuit with its coils nearby the LEDs, the magnetic flux induces currents in them which power the LEDs, transferring power wirelessly. You could increase the distance they do so by tuning the circuits to match their resonant frequencies, but I guess that's for another video. That's all for today guys. I hope you are able to learn something new from today's video. If you think you did, please don't forget to hit that like button and share the video with your friends. If you think my channel has earned it, please consider subscribing if you haven't already and click that bell icon so that you get instant notifications of the videos I upload. Thanks for watching. Until next time, Remember, engineer, experiment, educate.